Hello friends, my name is Tejendra Jangal. Here I am discussing the objective solution of P.S.Bimbhra for synchronous machine from question number 21 to 30. Next video is coming soon for the transformer and coming soon solutions are power electronics for P.S.Bimbhra, AMFT and SADQ, unsolved problem of electromagnetics, SOMS outline series and many more. So don't forget to subscribe Reference Tech Education. Now come to the question number 1. The flux per pole in the synchronous motor with feed circuit on and the stator is disconnected from the supply is found to be 25 milliweber. Okay, when the stator is connected to the rated supply with the field excitation unchanged, okay, then the flux per pole in the machine is found to be 20 milliweber. Okay, while the motor is running at a no load. Okay, assuming no load losses to be zero, no load current drawn by the motor from the supply is led by the supply voltage, in the phase with the supply voltage, or it's zero. Now come to the solution. This is the simple question. Now at leading power factor, we draw the phasor diagram. Okay, in the generator this is the emf one, and the emf generated mmf, this is the mmf, and emf generated by the generator field winding is, in stator winding is led by 90 degree from E equals to n d5 minus n d5 by dt. Okay, and the at the leading power factor the generator current is lead by the angle phi. Okay, that is the power factor, input power factor angle. But in the motor, in the case of motor, the generator current Ig equals to minus Im. So the in the reverse direction, current is flowing in the reverse direction in the in case of motor, but both are equivalent. Okay, so the current in this direction. Okay, in the phasor. Now due to this current, FA is generated, that is armature MF. Now this armature MF is divided into two components, FA sin phi, that is demagnetizing component, and this is the cross magnetizing component. Now due to this demagnetizing component, the total flux is reduced per pole is from 25 milliweber to 20 milliweber. So at the at leading power factor, in case of synchronous motor, at leading power factor total flux is reduced. Okay, that way this leading power factor may be zero leading power factor or leading power factor. So the answer is the no load current drawn by the motor from the supply is lead by the supply voltage. So the answer B is correct. Now come to the question number 22. A three-phase alternator deliver power to balance the three-phase load power factor 0.707 lagging. It is observed that open circuit EMF phasor leads the corresponding terminal voltage phasor by 15 degree. Okay, neglecting the effect of harmonic, the angle between the axis of main field mmf, that is ff, and axis of the armature mmf, that is fa, will be 30 electrical, 60 electrical, 90 electrical, 150 electrical. Now come to the solution. This is the simple question. Now first we draw the phasor diagram of three-phase alternator in which this FF is the main field, and as mentioned in the question, the load power factor, that is theta, angle between the terminal voltage and armature current, that is theta, that is cos phi equals to 0.707, cos theta equals to 0.707, that is theta equals to 45 degree. Okay, and the open circuit EMF phasor, this is the open circuit EMF phasor, and corresponding terminal voltage. So the angle in between these two voltage, that is del, equal to 15 degree. Okay, as mentioned in the question. Now the total angle in between this armature mmf, that is fa, and ef is del plus 90, that is 60 degree, and the total angle in between the main field EF and armature MMF is 90 plus del plus theta, which is equal to 150 electrical. So the answer D is correct. Now come to the question number 23. A three-phase 400 volt delta connected alternator has the synchronous impedance of J20 ohm per phase. Okay, if it delivers a balanced load of 12 kVA at zero power factor leading, then percentage voltage regulation of the alternator is equal to. This is a simple question, but the concept is very important. Okay, this is the voltage regulation formula as we all know. Okay, now after delta to star conversion, the synchronous reactance XS equals to J20 by 3 and the phase power 4 kVA. The phase current at zero power factor is 4 kVA divided by phase voltage. Okay, that is 10 root 3 milliampere, 10 root 3 ampere. Okay, now come to the, now these value are put in the voltage regulation formula, then we get 15% voltage regulation. Okay, so the answer is B. That is wrong answer. Okay, now at leading power factor, excitation voltage is lower than terminal voltage. This is the main concept of this question. At leading power factor, excitation voltage, this excitation voltage is lower than terminal voltage, which can be found by the help of characteristics power factor versus field current characteristics. So this will become negative, so the answer A is correct. Okay, now come to the question number 24. A three-phase alternator has a negligible stator resistance. A short circuit test is conducted on this alternator. Okay, at particular speed, a field current if is required to drive the rated armature current. If the speed of the alternator is reduced to half, the field current required to maintain rated current would be equal to field if1 would be equal to 2if1 would be equal to if1 by 2 cannot be predicted due to the insufficient data. Now come to the solution. This is the simple question, but the concept is very important. Okay, this is the speed, synchronous speed, which is equals to 120 f upon p. So the synchronous speed is always dependent on the frequency. If the speed is reduced half, then the frequency will be also become half. Now we take the formula of armature current. What is armature current? The armature current is EF upon XS. Though both are the frequency expression. Now, after putting these expression, these become this expression is not frequency dependent. Okay, it is independent on the frequency. So the armature is always independent on the frequency. If the speed is reduced half, then the frequency is changed, but the frequency independent current, that is armature current, flow in the armature. So the armature current is not changed due to reduction of speed. So the answer A is correct. Okay, now come to the question number 25. A three-phase cylindrical rotor synchronous machine, effect of armature reaction is taken care by the magnetizing reactance. Synchronous reactance is equal to sum of mutual and leakage reactance. Effect of armature reaction is taken care by the armature reaction reactance. Armature reaction reactance and synchronous reactance is made up of armature reactance and leakage reactance, magnetizing reactance and leakage reactance. Now come to the solution. This is a simple question to understand. Okay, synchronous reactance is the sum of armature reaction reactance and leakage reactance. Okay, this is the armature reactance. Okay, and reaction is the phenomena in the armature reaction. Okay, so main concept here that the armature reactance may be reaction reactance or maybe magnetizing reactance. Okay, so effect of the armature reaction is taken care by the magnetizing reactance. Magnetic, this armature reactance is magnetizing reactance at zero leading power vector. Okay, so the statement first is correct, and statement 2, synchronous reactance is equal to sum of mutual and leakage reactance. There is no mutual reactance in the synchronous motor, synchronous machine. So statement 2 is wrong. Okay, the effect of reaction, armature reaction, is taken care by the armature reaction reactance. Yes, this is the armature reaction reactant, and this is the armature leakage reactant. So taken care by the armature reaction reactants. Okay,